Last episode, a matrix warped the whole space. Now zoom into two single vectors inside it and ask the everyday questions. How long is this one? And how much do these two agree? Length first. Imagine walking from the origin to a point. Go in a straight diagonal line, and that distance is the L2 norm, plane, Pythagoras. Walk only along the streets, block by block, and that taxicab distance is the L1 norm. Now agreement, the dot product multiplies matching components and sums them. When a vector dots with itself, you get its length squared. When two different vectors point the same way, the dot product is large. When they're perpendicular, it's exactly 0. Formally, a dot b equals the length of a times the length of b times the cosine of the angle between them. Divide out the lengths and you've isolated that cosine, the famous cosine similarity. And the projection of a onto b is a dot b over b dot b times b, the shadow a casts on b's direction. This shows up everywhere. L2 regularization penalizes the squared norm of the weights to keep them small. Cosine similarity ranks how close two embeddings are. And every attention score is a dot product between a query and a key, projections deciding what to focus on. Here's the whole thing in one file. We take two concrete vectors, measure their norms, their dot product, their cosine, and draw the projection of one onto the other. We define a and b as fixed 2D vectors, so the numbers are exact. We compute the L1 and L2 norms of a. We compute the dot product, and from it the cosine similarity. We compute the projection of a onto b and its length. We print every number and plot a, b and the projection, foot, length, angle and shadow, the three rulers of vector space. Next time we put them to work, finding the directions data spreads most, eigenvectors and PCA.